In the previous Ready, Set, Go assignment, you were finding the constant difference in an arithmetic sequence, and then we're using the constant difference to find the missing terms. This assignment is similar to that, but in this assignment, you need to determine whether the given sequence of numbers represents an arithmetic sequence or a geometric sequence before you can fill in the missing terms. If a sequence of numbers is created by adding the same number to get the next term, the sequence is called an arithmetic sequence, and the number that is being added is called the constant difference. If a sequence of numbers is created by multiplying the same number to get the next term, the sequence is called a geometric sequence. The number that is being repeatedly multiplied is called the common ratio. In the following examples, you need to find the missing values for each sequence, underline whether it has a constant difference or a constant ratio, state the value of the constant difference or ratio, then indicate if the sequence is arithmetic or geometric by circling the correct answer. First, subtract 8 from 19. 19 minus 8 equals 11, so the number 11 is the constant difference. 30 is the next number in the sequence because 19 plus 11 equals 30. You can check your thinking by adding 11 to 30 to get the next term. The answer is 41. Likewise, 41 plus 11 equals 52. The next number will be 52 plus 11, or 63. The sequence is an arithmetic sequence because it has a constant difference. Now let's try another sequence. First, check to see if the sequence is arithmetic. Subtract -1 from -4. -4 minus -1 is the same as -4 plus 1, which equals -3. If this is an arithmetic sequence, you should get -3 when you subtract -64 from -256, but you get -196. It's not arithmetic. Try finding the common ratio. To find the common ratio, divide -4 by -1. The quotient is 4. Next, divide -256 by -64. Again, the quotient is 4. The number 4 is the common ratio. The number following -4 in the sequence is 4 times -4, or -16. The number following -256 is 4 times -256, or -1024. The sequence is geometric. For each task that you have been doing in class, you have been asked to find a recursive function rule and an explicit function rule that corresponds to the changing pattern. These two types of equations can help you predict the next term in a sequence, or a term that is many steps away from the one you have now. The set portion of the last task focused on writing just the recursive function rule for both an arithmetic sequence and a geometric sequence. The recursive function rule is best used to predict the next term. All you need to know is how much to add to the one you have now, or what number to multiply by the one you have now. The explicit function rule is used when you don't have the previous term, or you want to predict a term that is many steps from the one you have. If you need help writing the recursive equations, refer to the explanation in Ready, Set, Go 1.6. The explicit equations for arithmetic sequences and geometric sequences are based on the rules for repeated addition and repeated multiplication. The sum 5 plus 5 plus 5 can be written as 3 times 5, and the product 5 times 5 times 5 can be written as 5 to the third power. In the following examples, you need to determine whether the given information represents an arithmetic or geometric sequence. Then you need to write the recursive and explicit equations for each. This sequence could be rewritten in the following table. Term 1 gives us 5. Term 2 gives us 13, or 5 plus 8. Term 3 gives us 21, or 5 plus 8 plus 8. Term 4 gives us 29, or 5 plus 8 plus 8 plus 8. Notice that term 1 gives us 5 plus 0 eighths, term 2 gives us 5 plus 1 8, term 3 gives us 5 plus 2 eighths, and term 4 gives us 5 plus 3 eighths. Rewriting the terms in this manner helps us to see the repeated addition. This is an arithmetic sequence. The explicit equation has 1 5, and it's going to contain some eighths. The next thing to determine is how many eighths and how the number of eighths relates to the input number. When the input is 1, we have no 8s, or 1 minus 1 times 8. When the input is 2, we have 1 8, or 2 minus 1 times 8. This pattern continues. If x is the input number, then the output number is y equals 5 plus x minus 1 times 8. This is an acceptable explicit equation for the sequence. It is also acceptable to simplify the equation by distributing the 8 and adding like terms. Y equals 5 plus x minus 1 times 8 is the same as 5 plus 8x minus 8, which is negative 3 plus 8x. The equation y equals negative 3 plus 8x is an equivalent explicit equation. Let's do another example. This sequence could be rewritten in the following table. Term 1 gives us an output of 5, term 2 gives us an output of 20, or 5 times 4, term 3 gives us an output of 80, or 5 times 4 times 4, term 4 gives us an output of 240, or 5 times 4 times 4 times 4. Notice that term 1 gives us 5 times 4 to the 0 power, term 2 gives us 5 times 4 to the first power, term 3 gives us 5 times 4 to the second power, and term 4 gives us 5 times 4 to the third power. Rewriting the terms in this manner helps us to see the repeated multiplication. This is a geometric sequence. The explicit equation is going to contain a 4 raised to a power. Can you see a pattern in the number of times 4 is multiplied at each step? Once again, you want to relate the step number to the number of times 4 is multiplied. The exponent seems to be always 1 less than the step number, or x minus 1. In addition, then the output number is y equals 5 times 4 to the x minus 1 power. In this problem, 2 points and a slope are given. Plot and label the 2 points on the graph. Draw the line segment between them, then sketch on the graph how you count the slope of the line by moving up or down and then sideways from one point to the other. Let's start by graphing the points G, which is negative 3, negative 4, and point H, which is 4, 2. If you don't recall how to graph points, refer to the Go section in Ready, Set, Go 1.1. Slope is often defined as the rise over run. A lowercase m is commonly used to denote the slope. It helps to write the slope as a fraction even if the bottom number is 1, because slope is a description of how much a line goes up or down each time you move left or right. Count the spaces from point G up to the horizontal line that goes through point H. The number of spaces that you move up or down is the rise, or the top number of your fraction. Count the spaces right or left until you reach the vertical line that contains point H. This is your run, or the number that goes on the bottom of your fraction. It doesn't matter if you count the rise first or second, as long as you place the number in the correct position in the fraction. Notice that the segment connecting these points has a slope of 6 over 7.